Hello, I wanted to go over a few things about sampling distributions. First, the sampling distribution of the sample mean, and then the sampling distribution of the sample proportion. So one of the biggest aspects that we will see regarding both for the sample mean and also later the the sample proportion, although this is mainly the first aspect of it, at least, being shown in this particular section. So for example number 1 on here, I have about an intelligence quotient is a measurement of intelligence derived from a standardized test, such as the Stanford-Binet IQ test. Scores on this test are approximately normally distributed with a mean score of 100 and a standard deviation of 15. And we want to know about the sampling distribution. I first have on here about a sample of size 4, but we will see a couple of aspects on this. So instead of StatCrunch, underneath applets on here, we can do a sampling distribution and be able to find different aspects of it. So now I'm just going to choose a skewed one here to begin with. Now, if we choose a small sample, let's do 4 first. And then, let me do 4 first. And I do that a couple of times. Right, I just did 1. That will just show a little bit on here. If we do 5, that will slightly speed that up a bit. Again, nothing really dramatic about that, right, so far. As I let this play out for the total of 4 samples that I chose. For the total of, 5 samples that I chose. As you can see, nothing really drastic. If I do it, a whole bunch of times, notice how that doesn't really look like anything too special. Looks just like that basic right skewness that we have on there. But by that central limit theorem, if we have big sample sizes, specifically for the sample mean, big sample sizes will be such as 30 or higher. And if we do that a whole bunch of times, notice what happened to our sample mean distribution down here. That looks a lot more like a normal distribution than a skewed right distribution. And likewise, if we go even higher, let's do like 100, it's becoming more and more and more approximately normal. The same thing will happen to a skewed left, or basically any distribution. Now, the mean and standard deviation of the sampling distribution has a mean. The mean of that sampling distribution will be equal to the population mean, and the standard deviation of the sampling distribution will be the population standard deviation divided by the square root of the sample size. And then we can go over a couple of examples on how to do it here inside of StatCrunch. So, first and foremost, if we have those IQ scores from before being normally distributed with a mean of 100 and standard deviation of 15, we want the probability that a simple random sample of size 10 results in a sample mean greater than 110. So now, in order for us to do that, we need to look at that sampling distribution. So, this uses, as I put this on here correctly, this will use then, this will use, since this is indeed normally distributed to begin with, we're going to have our mean of that sampling distribution being equal to that population mean of 100. And then the standard deviation is going to look like that population standard deviation of 15 divided by the square root of the sample size, or 10. And then this value when we try to calculate it, it's going to give us a value of about 4.743. So 4.743. Now we want the probability that the mean of that that the mean of this simple random sample of size 10 is greater than 110. So greater than 110. And specifically, if we look at the normal curve for this, let's give a very rough sketch of that. If, let's say, right here is 100, and let's call 110 over here. We want the area to the right of this. So instead of StatCrunch, we're going to go to Stat, Calculators, and since we're talking about a normal distribution here, we'll go to Normal. And we have a mean here of 100. Standard deviation of that 4.743. And that's a strange pop-up. We want the X bar to be greater than 110. And that value, as displayed here, is going to be about 0.0175 for that probability in this area in this rightmost tail of the normal distribution. So again, for the sampling distribution about the sample mean, that central limit theorem will apply for us when we have sample sizes greater than or equal to 30. So such as in this example here, the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9. Weight gain during pregnancy is skewed right, but an obstetrician obtains a random sample of 35, which is greater than 30. So by that central limit theorem, the sampling distribution should be approximately normal. And she determines the mean weight gain during pregnancy was 36.2 pounds. We want to know, does this suggest anything unusual? So for something such as this, again, we're looking at the sampling distribution. So the mean is going to equal to 30. And the standard deviation equal to 12.9 divided by the square root of 35. Now, when we try to calculate that value, we are going to get a value of 2.18 about. And we want the probability with X bar and the weight of 36.2. Looking at the normal distribution again. Again, very rough sketch. Call the mean about here of 30. 36.2 will be over here. So, since we want to know if this is unusual, we want to find out the area above that point. So this would be a greater than. And when we plug this into StatCrunch, again, in that same normal calculator, we are going to get a value of we are going to get a value of 0.0022. Now, using a level of significance of 5%, this 0.0022 is indeed lower than 5%, so yes, this is unusual. Okay, so then moving on, we want a simple random size of 64, obtained with a mean of 79, standard deviation of 16. We want to describe the sampling distribution of X bar, since 64 is well greater than 30. This should be approximately normal. Approximately normal. If this was to write one of these days. The mean of the sampling distribution is just going to be 79. And the standard deviation is going to be 16 divided by the square root of 64, which just equals 2. And we have a whole bunch of values. So, first for the probability of X bar being greater than 82.5, let me do that one over here. So again, a very quick sketch of this normal distribution. We have our mean is 79 here. And 82.5 over here. We're talking about this area underneath here. So throwing that into our calculator. So 79, 2, and greater than 82.5. This will give us a value of 0.0401. And then for the probability of X bar being between 76.8 and 83. So then that rough sketch looks like, again, with 79 right here, then 76.8 over here, and 83 over here. We are referring to this entire area underneath the normal curve. So then, switching the normal calculator and StatCrunch to between, we are using those same values of 79 and 2 for the mean and standard deviation respectively, and just plug 76.8 and 83. And then, coincidentally, we got a much larger probability now of 0.8416. Now, for a simple random sample of size 10, obtained from a population with mean 68, standard deviation of 16, assuming the normal model can be used, we want the probability of X bar being less than 72.4. So then the mean of the distribution, 68. Standard deviation of the distribution being equal to 16 divided by the square root of 10. Throwing that into a calculator, we will get a value of about 5.06. Let's round that too. So 5.06. So the probability of X bar being less than 72.4, which again, a very rough sketch of the normal distribution, mean being right here of 68. We want 72.4, let's say here-ish. We're talking about the area under the normal curve of over here. Okay. So switching this back to the standard calculator and just throwing these values in. So 68, 5.06. This would be a less than 72.4. And we receive the area under the normal curve to be equal to 0.8077. Then lastly, for the sampling distribution of the sample mean, we have that the reading speed of second grade students is approximately normal, with a mean of 90 words per minute and a standard deviation of 10 words per minute. We want to know about the probability a randomly sorted student will read more than 96 words per minute. So based upon the way that this is written, we're talking about a randomly sorted student. We have the probability that that randomly sorted student will read more than 96 words per minute. But since we are not referring to the sampling distribution, this particular example just uses the mean of 90 and standard deviation is given of 10. And then for a rough sketch of that, actually before I do the calculation, will look something like this, with a mean of 90 here, 96. Talking about the tail over here. If my picture was drawn better. But throwing that into StatCrunch, so 90, 10. I want this to be greater than, and then 96. Okay, so that'll give a value of 0.2743. But now, for the probability of random sample of 20 second grade students has a mean reading rate of more than 96 words per minute. So based upon the same drawing, same probability statement, we now need to look at X bar as opposed to just X being greater than 96. Again, the mean of that distribution is going to be equal to 90. And the standard deviation of the distribution is going to be 10 now, divided by the square root of 20. And we need to calculate that value. So 10 divided by the square root of 20 will give us a value of 2.236. So 2.2336. Okay, 2.236 for that standard deviation. So we are going to change this to 2.236. Everything else stays the same. And do notice, since we have such a lower standard deviation now, this area under the normal curve is significantly lower than the original one. So 0.0036. will be that probability. Now there's a 5% chance that the mean reading speed of a random sample of 22 second grade students will exceed what value? Which I actually need to provide a little bit more space to actually write that one out. So let me just insert a little bit more space down here. If we want to, which we don't. Okay. Fine. I'll just make do. So the 5% chance the mean reading speed will exceed what value? We're trying to find that value. Unlike the one that we were just on, we do need to change the standard deviation, which will now be, let me do over here, equal to 10 divided by the square root of 22. This value, which will be slightly different than the one that we just calculated, 2.132. So the standard deviation, 2.132. So, and then the probability statement of this is going to be that the probability that x bar is greater than some number, we don't know what that is equal to 5%. So, changing this standard deviation to 2.132 and putting the 5% into the box to the right of the equal sign, we get ourselves a value of 93.51. Let's round that too. So this value in here, it's going to be 93.51. 93.51 for the probability to be 5%.